Hey everybody, welcome to video for Module 13, Section 3. We're going to be talking about special right triangles, and we're doing this at the start of our trigonometry unit, which we'll dig into a little bit more as the unit goes on. So first off, what is a special right triangle? It's going to be a triangle that has certain conditions that hold true for its side lengths and its angles. So let's look at this explore together. For part A, it says the figure shows an isosceles right triangle. Identify first off the base angles and use the fact that they are complementary to write an equation relating their measures. So what we're going to do here is we're going to realize that because this is an isosceles triangle here, remember base angles are at the ends of those congruent sides. So we're going to say that the base angles are angle A and angle B. And if angle A plus angle B plus the 90-degree angle that was there already are going to equal 180, then that means that angle A and angle B together equal 90 degrees. Now we also know that in any isosceles triangle, you guys, the base angles are marked congruent, remember. So that means that angle A and angle B are exactly the same measure. So essentially we could do a quick substitution here, and we could say 2 angle A's if you wanted to, or 2 angle B's would equal 90 degrees. And so as soon as we know that that is true, we know that each of the base angles themselves are 45 degrees by a quick division. So because of this result of two 45-degree angles, in part C we can write 45 degrees and 45 degrees. And moving on from now, you guys, we're going to refer to this type of isosceles right triangle as the special right triangle of type 45, 45, 90. Okay? If you hear me talk about a 45, 45, 90, you know we're talking about an isosceles right triangle. So what we're going to do next is we're going to look into whether there's a special relationship between the two legs of these isosceles triangles and the length of the hypotenuse. And of course, we're going to find that that is definitely the case. So here's our hypotenuse, remember, across from the right angle. So in part D, we're asked to use the Pythagorean theorem to figure out the length of the hypotenuse in terms of the length of each leg. So let's use that. If we said leg squared, or x squared, plus leg squared, or another x squared, is going to equal the hypotenuse squared, and we'll go ahead and keep that as h. Then let's see if we can simplify. X squared plus x squared is, of course, 2x squared. So if 2x squared equals h squared, then I'm going to be taking the square root of both sides of that equation, and we would get then the square root of 2x squared is equal to h. And remember, we can pull off the square root of 2 and the square root of x squared as two separate factors for h. And one of those pieces does simplify. It's the x that simplifies. The square root of x squared simplifies, that is. And so we have h equals x times the square root of 2. So this is an important formula for you guys to keep in mind, that the hypotenuse is always whatever that leg is, x standing for the leg, times the square root of 2. Okay, now let's look at the next page. Here I'm on page 710, and we're going to investigate another type of special right triangle. And this comes from a right triangle that's formed, as you can see here, as half of an equilateral triangle. So let's go ahead and mark the sides that we can here. We know this is isosceles AB is equal to DB, and of course we've got congruent base angles just like we did before, and we have a nice shared side here. So what we can determine is that, of course, in an equilateral triangle, the measure of angle A is going to equal 60 degrees, so is the measure of angle B, and so is the measure of angle D, although we need to call the measure of angle B the measure of angle ABD. And therefore, the measure of angle ABC is, again, looking at just 1/2 of this equilateral triangle. So this angle here, ABC, is going to be half of 60, or 30. And, of course, we know the measure of angle D is also equal to 60. And the measure of angle C, or ACB, is equal to 90. So the three measures that we're looking for there, again, coming from just triangle ABC, okay, is going to be your angle A is 60, your angle ACB is 90, and your angle ABC is 30. Now we know that the two halves of this triangle, of course, are congruent. If we were to go ahead and explain why, you guys can see, I think, the two hypotenuses are congruent, or hypotenusi. I always forget what the plural of that is, but the hypotenuses are congruent. And then we have a shared side here that happens to be a leg, and it's a right triangle. So you can either use angle, side. Oops, let's get my writer back here. You can either use angle, side, or hypotenuse, leg, to prove that those triangles are congruent. So we call this type of special right triangle, just like the last one had a special name, we called it a 45-45-90 because we're naming its angle measures. This one, you guys, becomes a 30-60-90, using the idea of, again, what are the angle measures that we have. So let's see if we can investigate now the lengths of these sides and if there's a relationship. So part C says, and they've pulled off in the diagram to the right there, just triangle ABC from the diagram above. But it says, let the length of AC be x, and you can see that's the label. What does that mean the length of AB has to be, and why is that? Well, you guys remember, in the bisected base there of AD of this isosceles triangle, AC is really just half the length of AD. So if AC is 1/2 also of AB, which is half of the length of BD, okay, then X gets set equal to half the length of AB. And remember, we can plug in any of these sides, AB or BD, in the place of what AC is half of, because all three sides of our triangle are congruent because it's an equilateral triangle. So now we're here, okay? We've got that the length of AC, which was given to us, we're calling X. If that's half of AB, then how do we solve this equation for AB, you guys? Well, we just multiply both sides by 2, and so we get that 2x could be expressed algebraically as the length of AB. So let's go ahead and put that onto our diagram. And that makes sense, I hope, that if this came from an equilateral triangle to begin with, and this is the long side here across from the right angle that was the initial side of the equilateral triangle, then this AC, remember, only represents half of that bottom distance. So that's why that works out. Now, just like before on page 709, as we use Pythagorean theorem to figure out the length that's missing here, the length of BC, this is what we're going to see. So I'm going to scroll up here so we can just focus on the diagram that we have in front of us for C. And using Pythagorean theorem, and you guys, I'm going to call this BC length A, we'll say. Then if we use Pythagorean theorem, we could say that A squared plus the other leg, which happens to be x, all squared, would equal the hypotenuse, which is 2x, all squared. Keeping in mind we have to square both the 2 and the x in that parenthesis there, we get a squared plus x squared equals not 2x squared, but 4x squared. We got to square the 2 and the x, okay? Then if we're going to solve for a, remember, or the length of BC, we're going to subtract x squared from both sides. So we have that a equals 3x squared, a squared equals 3x squared. And then just like before, we're going to square root both sides there. And notice what happens is that we can pull off again the square root of 3 as a factor and the square root of x squared as a factor. And the part that simplifies there is the square root of x squared. So a is going to be equal to the square root of 3 times just x. And again, that's a multiplier between that radical and the x. And a reminder to you that that x, again, represents the leg length. Now, we have to be careful here because the legs were the same length with a 45, 45, 90, but in a 30, 60, 90, they're not anymore. So my x, we need to make sure we're referring to that as the short leg, and then a we're going to refer to as the long leg. And you guys will probably see me abbreviate that as LL for long leg and SL for short leg when we're working with these on the board. But that's the pattern that we're going to see for a 30, 60, 90. Let's review. The short leg is half the length of the hypotenuse, and the long leg is the same thing as the short leg times radical 3. Now that always works no matter what starting values we might have, as long as we know it's a 30, 60, 90. So we're going to use some problems next and see if we can apply those relationships. Before we get to some application problems though, you guys, I want to take a look at number 4 here on page 710 where we're explaining the error. This is a common thing that I see as a teacher. And it even took me a little while to find the error because I see it so often from students like you guys. So I just wanted to point out here that, remember, just because the leg is times radical 3 to get the long leg length, the short leg times radical 3 to get the long leg length, doesn't mean if I automatically just see a radical 3 in the long leg length, and remember, I know it's the long leg because it's opposite the 60-degree angle, because that's the larger of the two acute angles, so it's the longer leg. Just because I see a radical 3 as part of the number does not mean necessarily that the problem has been done correctly. So I just wanted to show that to you here. There is no way, you guys, to solve this the way that this person has labeled it, because number one, 6 times radical 3 is something bigger than 6, okay? If I were to do that decimal out, you could see the decimal for 6 times radical 3 is very definitely bigger than 6. So that means it can't be a leg if it's the longest side. It should be the hypotenuse. 6 is the hypotenuse, which, remember, is meant to be the longest side. So the question is, how do we correct it? Well, remember, we take the long leg as the short leg times the square root of 3, and the short leg is not 6, it's 3 times the square root of 3 gives me the long leg. So that should be my correction there, okay? Don't just see a radical 3 and call it good. All right, let's move on to application. In Explain 1, we have here our two special right triangle relationships. Put big fat stars next to both of these. You definitely want to make sure that these get memorized. And here we are again stating them with their names as we've called them, 45, 45, 90, and 30, 60, 90 triangles, because we call them by their angle measures. We found out the hypotenuse was the square root of 2 times one of the leg lengths, doesn't matter which one, because in a 45, 45, 90 it's isosceles, so both legs are the same length. And in a 30, 60, 90 we have 3 different lengths, so we have the short leg, which is just x, the long leg, which is the short leg times radical 3, and I'm going to go ahead and write that there for you guys. And then the hypotenuse, which is 2 times x, or twice the length of the short leg, okay? So let's keep all that in mind, and let's use that to fill in what we have here for example 1. Example 1 says, find the unknown side lengths in triangle ABC. Well, this is a 45, 45, 90, and we know that the hypotenuse is square root of 2 times as long as each leg. So this says substitute 10 for AB in this equation, because we know the length of AB, or the hypotenuse, is each leg times radical 2. The one that we are interested in, of course, is the leg length that's missing. So we really don't need both sides of this. We can kind of ignore the whole second side of that and just set it equal to the equation. The next thing that the book asks you to do is multiply by radical 2 and then divide by radical 2, or divide by just 2. I'd like to modify these steps if we can and talk about just simply, instead of multiplying by radical 2, we're going to think of dividing by radical 2. So we'd have 10 divided by radical 2 equals AC times radical 2, also divided by radical 2. And we know that those radicals would disappear, but that this side, 10 divided by radical 2, remember, we cannot leave the radical in the denominator. So again, I would modify the next step. Instead of writing divide by 2, we would say the word rationalize. And the word rationalize simply means get the radical out of the denominator. And then I would add also, after you rationalize, simplify the fraction that you have. So I'm going to take this division up here so we have a little more room, you guys. If we do 10 divided by radical 2, we know we can't leave the radical down there. So we're going to multiply by 1, but the version of 1 that we're multiplying by is radical 2 over radical 2. Remember, any number divided by itself is 1. So we haven't changed the value of this initial fraction, we've just changed how it looks. Then, when I have a fraction times a fraction, I want to always multiply across numerator times numerator and denominator times denominator. So I will get 10 radical 2, 10 square root of 2 if you will, divide by 2. And then what I mean by simplify, I mean, well, 2 goes into 10 5 times. So this final answer here is that AC and BC are both 5 times the radical 2. In part B, we have example 1, part B, that is now a 30, 60, 90 triangle that we have to begin with. And we have information that we're given. Looks like EF is given to us. And since that's opposite the angle of 30 degrees, we can say that EF, or 5 radical 3, is qualifying as our short leg here. So our hypotenuse is twice as long as the shorter leg. DE is twice the length then of EF. So we're going to substitute the value 5 radical 3 for EF, and then DE is 2 times 5 radical 3, which makes DE 10 radical 3. So let's write that on the diagram. And we can still see the relationship that this is twice the short leg. Now the longer leg, we want to simply make square root of 3 times as long as the shorter leg. So in this case, DF is the longer leg we're looking for, and that's going to be the length of EF again times radical 3. We're going to substitute the length we know for EF, and DF comes out to be 5 radical 3 times radical 3. Now we know that that is 5 times radical 3 squared. And you guys, what happens when we take the square of a square root? It kind of undoes itself and we get the number under the radical symbol. So this is just 3, this part right here. This square of a square root just comes out to be 3. So this product is 5 times 3, or DF equals 15. So that's our application problem. On the next page, we want you to go ahead and do your turns number 5 and 6, seeing if you can find the missing side lengths of each of these special right triangles. We're going to do lots of practice with this the next time we're in class, but let's see what you can do with just these 2 basic examples, okay?